Recall that the one-to-one system can be illustrated by these four-step cumulative curves. So we can see from the figure the decisions for this system is when to dispatch a vehicle. That is this time decisions for dispatch. Typically, the production line and then the consumption line are given. Definitely, we do not know how customer consume the product. Typically, the consumption will be forecasted or based on some other information. Then, the constraint is that all the consumption should be satisfied. That is, under a certain transportation method, the arrival line should be always above the consumption line. That means arrival line has to be above the consumption line. Okay, and then the objective of the problem is to minimize the cost. So let's see, where are the costs? In fact, there are two types of cost we can see from the figure. One is the cost where the products are stored, or the waiting cost, or the holding cost. We can consider all these ranges. So this dashed line indicates the product is stored at location A. And then this dashed line tells us the products are saved at location B. And then this cost, typically we call it holding cost. Remember that we need to send a truck or some other transportation method to move the product from location A to location B. So this incurs the transportation cost. And then all the task for this one-to-one system is try to minimize the cost. Find the best decisions for dispatch. So the cost equals holding cost plus the transportation cost. Okay, now let's first handle the holding cost. Before rigorously formulate the problem, we need to make some assumptions. The first assumption is that the production line and then the consumption line are all straight lines. So that means the demand rate for the consumption and then the production rate at location A are a constant. For example, we produce milk 1 gallon per day for every day. That's a constant. So in this case, the cumulative curve for the production and the consumption are all straight increasing lines. So we denote the constant production rate and consumption rate as D prime. Another assumption is that the headway for each dispatching are equal. That also means the load are equal. So these are equal. These are equal. So by this assumption, we can simplify the problem and then provide a relatively analytical formulation. So let's denote this headway to be h. Also, we want to mention for each item, we assume that the system follows first in, first out rule. So that means for a produced item, if it arrives early, it will be consumed early. And then to analyze the holding cost, we will focus on these triangles. Because we'll assume the production line and the consumption lines are straight lines, so their demand rate will be also the same. And then because we assume the headways and load are the same for each dispatch, so all these triangles are also the same. Okay, so in this case, our analysis for the holding cost will be focusing on these small triangles. Remember, this line is in location A. This line is in location B. So the holding cost may incur at either location A and location B. To store the item, typically there will be two parts of cost. First one is the rent cost of the storage place. And then the second one is the inventory waiting cost or inventory penalty cost. For example, your milk may be bad. We call it inventory waiting. So let's discuss the rent cost and then the waiting cost one by one. For the rent cost, intuitively, this cost incurs when you rent a storage room. So it should be a cost term related to the maximum capacity for this renting space. Remember that we have assumed like all the triangles for dispatching are identical. For, let's see, this is on location A. Okay, so the production rate are the same as the demand rate, D prime. And then this is the time between two dispatches. So this is H. And then this is a load. You can see the load equals to H times D prime. So the rent cost should, based on the space you rented. Let's see, we define the rent cost per unit space you rent. Let's see, R is for rent. Let's see, this is a cost. Let's see, dollar per year if you rent a unit space. Okay, so then in this case, your total rent cost 1 year. So in 1 year, the maximum space should be at least this load size, right? So in 1 year, your rent cost should be your dollar per year times this load. Okay. And then you may want to calculate the prorated cost per item. So you can see in these triangles, let's see, if we will give the production or the demand rate D prime, it's also over 1 year, right? So this is a consumption rate is also given by the items consumed per year. Then you can have each item So the prorated rent cost should be the total cost divided by the total consumption or total production. Here at location A, right? So we call it total production, right? So this is a total cost 1 year. This is a total demand 1 year. Okay, so this gives you the unit rent cost per item. Okay, so interestingly, you can see that this rent cost per item is related to the headway and not related to our demand rate. Next, we discuss about the inventory waiting cost. So this inventory waiting cost is related to how long you store how many items in the storing place. So let's see, we have one triangle at location A. This is H. This is D prime H. And also we have another triangle, the same, but with a different direction. This is at location B. This is also H, D prime H. And then we have this transportation time. For example, let's denote this by Tm. Okay. And then for each item, for example, this is one item produced at a specific time. Depends on when it is produced, how long it will be stored based on the previous dispatch time. So this item will stay on location A for this amount of time. And then it will be on the way for Tm, transportation time, and then it will arrive at location B, and then keep staying at location B for another period of time. So if we treat all the items equally, and then we also treat the storage at location A and location B kind of equally. So you can see each item spans TA, Tm, and Tb. So the total time spent by each item T equals to Ta plus Tm plus Tb. And by the symmetric properties, we can know that this equals to the headway plus Tm. Okay, if we define the unit inventory waiting cost to be CI, this is dollars per item per time. Okay, so you can see there are how many items stored in this dispatch. Let's see if we calculate the total inventory waiting cost in 1 year. Okay, so we have D prime, the total items is d prime, and then the total time spent for each item is t, and then times the unit cost. Or we can write it in that is a cost, inventory waiting cost per year. And also we want to calculate the waiting cost for each item. Similarly, we will divide this by the total demand. So this gives us CIT, or you can write it in H plus TM. Okay, so this gives us the waiting cost, right? Inventory waiting cost per item. So currently we assume that the inventory waiting cost incurs at both location A and location B, but sometimes people may not pay the inventory waiting cost at either location A or location B. For example, let's consider we are shipping human beings. Consider that this is like a bus, and then we ship human beings from station A to station B. So at station A, people are accumulated, but then when the bus arrives at station B, then human beings can just depart from station B. In that case, there's no need to pay this inventory waiting cost at station B. So the travel time for human beings are somewhat equals to TA, they are waiting at station A, plus the transportation time. So there's no waiting time at station B. So in this case, the total travel time for each person can be different. It varies based on how close they arrive at station A to the bus arrival. So in this case, we can calculate their average travel time. That is half of this headway, and then plus the transportation time. So by doing this adjustment, we can see the inventory waiting cost for the cases where either we do not pay the inventory cost at location A or the cost at location B can be adjusted by a half factor times that's the headway. So there are different cases we can consider based on if we count the cost at both locations or we only count one location. Now we can calculate the total holding cost. And remember the total holding cost has two terms. One is run cost. One is inventory waiting cost. So we have derived as the run cost per unit item. Let's see, per item, CRH, and then the inventory waiting cost, CI, H plus PM. Okay, so then we can get the total holding cost per item equals. Okay, so sometimes we may combine the first two costs together because they are a function of the headway, and then leave the last term separately. So sometimes we call the first part, because it's a function of the headway, call it a stationary inventory cost. And sometimes we call the second term, which is independent of the headway. This term reflects that the cost spent on the transportation. So we call this a pipeline inventory cost.